Myself. Hi, thanks a lot for inviting me. I'm Kate Saenko, and I'm from Boston University. I wanted to, talk about some of our recent work on this issue of dataset shift, sort of broadly, and I'll talk about, I think, roughly 3 recent papers. Feel free to unmute and ask me questions. I think it's a small enough group that we can always customize this to whatever you guys are more interested in. So we just hide these meeting panel controls. So so data shift happens is the title of my talk, and really the point of the talk is what can we do about it if we accept the situation that data shift, in particular, some shift in the input data and in fact also label distributions is very common in many applications of machine learning and computer vision and AI. So it's not really an issue of will it happen? It will happen, but what can we then do about it? So that's the theme of my talk today. First of all, why do we have this problem of dataset shift and dataset bias in general? Well, it's because data is expensive, right? If we had unlimited free labeled data for any problem we ever wanted, we wouldn't have this issue. We would just collect all the infinite amount of data and train our models on it. And so our training data will always reflect the target distribution of data that we're going to be tested on. But that's not the case in real life. In real life, collecting data is very expensive, or collecting a large amount of data is very expensive. It's time consuming. Sometimes it's not really feasible. Sometimes it requires expert annotators that are very expensive or not available. And there's also the long tail category distribution that we often have to deal with, where it's just hard to find enough examples of certain categories or labels that we're after. Excuse me. So this is what leads to this problem of dataset bias that I've personally been looking at since more than 10 years ago. Sad to say, I still don't feel like I've solved this problem. Still working on it. So basically, we have some data set that our AI is trained on. Let's say it's detecting pedestrians, and we train it on data set collected somewhere in California. And then when we deploy it in a new location, let's say New England, where now it's asked to label data from a different distribution that it was trained on, it starts to have problems, missing detections, in general, lower accuracy, right? So this is the essence of the problem. This happens because the kinds of data or data set that the model is trained on doesn't quite match the data that it's being tested on. So we call it data set bias or domain shift. There are different ways to refer to this. Often, more recently, people also refer to these issues as robustness. But I want to be clear that robustness is a more general term and often also includes robustness to adversarial attacks, which it is a kind of domain shift or dataset shift or dataset bias, but kind of a very specific sense of an adversary trying to create an adversarial example. What we're going to talk about today is natural domain shift. There's no adversary. This just happens naturally, right? Like, so your car will encounter new locations when you start deploying it in different cities all over the country, right? So there's no adversary trying to trip up your model. It's just going to see new data. So, the issue that we are still having in machine learning is the vast majority of our data sets are tested in an IID manner, right? So we just have an IID test set identically distributed to the training data. We train the model on the training set, we test it on the same distribution test set, and we say, great, this worked well, it beat the baseline. But this really is a bad estimate of generalization of our models, I believe, because it overestimates, how well our models generalize, because we're testing them on the same exact distribution they are trained on. 99% of all machine learning papers are doing this. Recently, there's a trend towards more testing on out of distribution data, which I think is great. But it's still the de facto standard is IID test sets. So in O.O.D data, right, we want the model to sort of be trained on this blue distribution, whatever training data we're giving it, which includes potentially even multiple underlying distributions like rainy scenes versus sunny scenes versus foggy scenes. But then at test time, we're going to give it a completely new distribution, which overlaps with the training data, right? So this is still, cars and roads, but now there's snow. It just snowed for the first time in Boston yesterday. I don't know if it's snowing where you are, but I witnessed my cat experience this problem. She's never seen snow before. She's 1 year old. And, it took her a while, but she adapted, right? So can our AI models also adapt to new kinds of data? So we've been developing various kinds of solution to this problem. The first class of solutions is what we call domain adaptation. So in adaptation, we are given labeled data, also called source data, and then we're also given unlabeled data, which we assume it's simple enough to collect unlabeled data. Let's say we just put a camera on the car and drive around. There's no labeling involved. This is relatively easy to get from our new target distribution, our target location, let's say. And now the task is to adapt the model trained on labeled data to this new unlabeled data distribution. So that's adaptation. The other sort of setup that is often looked at in the literature is domain generalization. Right, so here the model is given multiple source domains, and it has to generalize when it's tested on a new held out distribution without being able to train on data from that held out distribution. So in adaptation, the model can train on the unlabeled target data. In generalization, it cannot. And so in generalization, basically the model needs to somehow learn from the source distributions what should be invariant across domains, right? So often people train on multiple source domains with explicit constraints that forces the model to become invariant to the domain differences. Often people use data augmentation to build this kind of invariance into models, but that's essentially the two kind of broad categories of methods in this area. So just making sure I'm keeping track of time. Okay. So we have developed several data sets, and also the community at large has contributed several data sets over the years. Because the trouble with the reason why 99% of all machine learning papers don't test on O.O.D data is because you need to collect a data set that has multiple data distributions. And that's just not what we do. That's not our accepted standard for how machine learning data sets are collected. So to combat this, we've come up with a couple of benchmarks over the years. You can see, the evolution of these benchmarks from sort of smaller, around 4,000 images in 2010 to DomainNet, which in 2019, when it was released, had around 600,000 images and 6 different domains. And there's others, there's different versions of ImageNet that have different distributions. Essentially, often the differences in distributions are defined as either the style of the image, like clip art versus drawing versus a real image, or could be sim to real. So in the middle one, there's simulated images versus real images of the same objects. There's also data sets in NLP and other sort of other non-vision kinds of data that I'm not going to show here, but they've also been developed. So, okay. So why do we care about this? Again, it reduces accuracy, right? So when your model is trained on data like this and tested on the same distribution, say it gets 90% accuracy. And this is what we found in this paper from 12 years ago now. When we train the model on this top domain and then test it on the bottom domain, the accuracy dropped significantly, right? But you could say, well, that was 12 years ago. Things have improved. We have deep neural networks now. They work better, right? We have bigger data sets now. Well, sadly, it hasn't quite improved to the point where we don't have an issue. So here is an experiment from a paper where they took ImageNet, the original ImageNet data set, and they collected a new test set for it. And they also saw a large, very large drop in accuracy, right? So 11 to 14% accuracy drop is huge, considering that improvements on ImageNet IID tests that were being measured in percent, 1% improvement is considered a significant improvement, right? But here, just by collecting a new test set in the same way as the original one, you see overall accuracy drop by this much. So still not a solved problem. So one thing that we wanted to look at is, okay, but we sort of haven't stopped with the supersizing of everything, right? Since that paper that I showed you, this paper called Do ImageNet Classifiers Generalized to ImageNet? So since that paper, we've seen kind of an impressive, just enormous explosion in size of our models. And so this is for language models. This is showing the size and number of parameters in billions of language models from 2018 to 2022 this year, right? So we went very quickly from under 1 billion to almost 1 trillion, and some have 1 trillion parameters. So how does this affect generalization to out of distribution data? In computer vision, the model size is also catching up. So Flamingo, shown on the left, has 80 billion parameters and has shown impressive gains on many zero-shot or few-shot problems, including that involve images and text and images, right? So problems like image captioning or visual question answering. So maybe now that we have these supersized models, we don't have this domain shift problem anymore. And also in terms of kind of data set size as well, right? So on the right, you see the number of parameters in the model definitely affects ImageNet top one accuracy, right? The bigger the model, the higher the accuracy. So what we wanted to see is what happens when we supersize the pre-trained model. And this was actually inspired by a competition that we run. So my group, we've been organizing this visual domain adaptation competition jointly with other groups over the years. So this is our 6th year of doing this. And we, this year we had, actually, no, this year was different. This is from 2021. So this was last year's competition. And what we saw was, so we asked participants to train on ImageNet. The source domain was ImageNet. And then the test set was different distributions of the same ImageNet objects, like drawings or ObjectNet, which is the same object as an ImageNet, but in kind of home situations, right? So not clean data taken online or from online websites, but ObjectNet data has often kind of strange poses, like this chair being sideways. And also we threw in some missing classes. just to make the adaptation problem harder, right? So we thought, okay, made this really hard. People better come up with some very cool new domain adaptation methods. But what we saw, in fact, when we looked at the winner, so the winner, the winning team, Baby Chick is the name of the team from Shirley Robotics. They won by a lot, if you look at the difference in the second and top performers, but they actually didn't do any domain adaptation. What they did was they took this BEIT model, which had just come out, and just took that backbone directly and fine-tuned it on the source, and tested it on the held out target domains, and it beat everything by a large margin. So said, okay, there's something going on here. Maybe, it's something because it's a larger model, it's using a transformer. Before, everything was using ResNets. So we wanted to explore this further, this kind of interesting result that we saw in our challenge. And so what we did was we said, okay, let's look at pre-training. Maybe the pre-trained model, its size and the data it's trained on, its architecture, maybe that is very important for generalization. So this was a paper that we just published in ECCV 2022 that was led by Dong-Yoon Kim and Kai-Hong Wang, co-authored with Stan Sclera at BU. So the goal here was to study pre-training as sort of this missing or often overlooked step for domain generalization and adaptation. Right, so if you look at the existing kind of pipeline for domain adaptation generalization work, what most people do is they pre-train on ImageNet 1K, they use a ResNet architecture, always the same backbone so that everything is compared to apples comparisons, right? And then after this pre-training stage, there's an adaptation stage. So this is where you come up with a model that adapts from the source to the target. But the input to the adaptation algorithm is always some pre-trained model. So what we wanted to compare is how about we replace the existing pre-training paradigm with more modern pre-training, with this larger data set, the supersized data, the supersized model, maybe a transformer architecture instead of CNN, the more modern architecture. Okay, so that's what we looked at. Now, I also wanted to look at pre-training, self-supervised versus supervised pre-training, how this affects generalization. So the long story short, the takeaway from this work was that pre-training and backbone definitely matter a lot. And perhaps it's not too surprising, given that we know that the strength of the source model is correlated with how well it generalizes. But just to kind of give you an idea, so these are accuracy numbers from existing domain adaptation methods. So these are all fairly recent papers, but now not super recent, but maybe from a year, 2 years ago, 3 years ago, that we're all using ResNet 101 backbones pre-trained on ImageNet 1K, and they're just using different adaptation methods. So ADA, MCD, these are older actually, but MSDA, SIMP-AI, these are all different adaptation methods. And you can see that, they, some work better than others. So green bars are multi-source, so train on multiple source domains and then adapt it to the target. And blue are single source. But if we now compare this to just replacing this ResNet 101 backbone with a more modern backbone, we use ComNext X large in this case, we see that just by replacing the backbone, not doing any adaptation at all, we get much better accuracy than all of these state-of-the-art methods, right? So there's definitely something going on. This is why, again, back to our challenge results, why our participants were able to improve on, many other teams who were still working with these older backbones, even though their adaptation method may have been much better. In fact, the winning team didn't even use adaptation, but they didn't achieve the same accuracy on the new targets. Okay, so digging into this more, we looked at whether or not the model size matters, right? So what happens when we increase the number of parameters in the model? And here, the different plots are different data sets. DomainNet is the one I mentioned earlier. There's also Office Home, which is, again, these are all computer vision data sets. Wild is cameras, wild cams, so recording from animal camera traps. CUB is also a fine-grained animal categorization data set. So these all have multiple domains. And okay, so the pre-training data set here is ImageNet 22K. So we increased the amount of pre-training data, and it's the same for all four. And we're also increasing the number of parameters. Sorry, still getting over a cold. And we see that the number of parameters increasing pretty much correlates with generalization increasing, right? So this is for training on one domain and testing on new domains. All right, so larger model, more parameters, better generalization to new domains. The next question we wanted to look at is, what about the architecture itself? Can transformers generalize better than CNNs? And here, the results were a little bit mixed. So we, in fact, saw that for some data sets, the convolutional architecture, so ConvNeXT is the convolutional architecture here, whereas ResNet 50 is the older convolutional architecture. It certainly doesn't do as well, but ConvNeXT takes all the tricks that transformers are using and applies them to convolutional networks. So it's a more fair comparison. And you see that when pre-training on ImageNet 1K, with roughly the same amount of parameters, ConvNeXT is much better. And in fact, it's better than SWIN transformer on certain data sets like DomainNet, but not always, right? So sometimes the transformer is better. So it's kind of a little bit mixed here. The results are a little bit mixed. On average, transformers were better, so 49.5 average performance when training on ImageNet 1K. And so this is for DEITS. It's one type of transformer. SWIN-T was slightly lower, but better than ConvNeXT. But again, not on all data sets. So in DomainNet, ConvNeXT did better. So this could be a good segue into more work looking at exactly what the differences are. And we actually have a paper at NeurIPS this year that tries to tease out more exactly what kinds of changes in the input data are transformers invariant to versus convolutional networks invariant to. And in that paper, we kind of looked at what happens when the pose of the object shifts or the lighting changes, illumination changes in the image, all of these kinds of things, occlusion. So I think there's more work to be done, definitely, but it's not a super clear, it's not like a very clear winner on the transformer side. All right, so the next question we wanted to look at is which pre-training data set is better for generalization. And here the takeaway message was that the bigger the data set for pre-training, the better the generalization. But this, and also text. So text meaning if we pre-train on image caption data sets, as is done in the CLIP model. But this is also not always the case. So there are exceptions to this rule, right? So if you look at the upper left, here we're testing the SWIN B transformer, And there are 4 data sets here, and we're comparing pre-training on ImageNet 1K in blue to pre-training on ImageNet 22K in red. So we're basically looking what happens when we increase the size of pre-training data from 1K to 22K. So it's more categories as well in 22K. And you see that pretty much universally generalization improves. For Connex B, it's the same trend. For EfficientNet B7, also the same trend. And when we look at VITB, now it's interesting to see that here, when we pre-train on, so here we're actually looking at the effect of image text pre-training. So instead of comparing ImageNet 1K to 22K down here in this plot, we're comparing ImageNet 1K to ImageNet 1K plus image and text. So image and text is the clip pre-training. And we see that adding image and text pre-training, the performance goes up for Office Home and Wild, but not, and DomainNet, but not for CUB, not this fine-grained animal data set. So it's interesting that, you know, as a rule, more data is better and image text helps, but not always, again. So more things to study here and more kind of interesting questions to look at. Okay, so finally, we wanted to see, well, what if we now take this more modern pre-training and then add domain adaptation methods on top of that? Will they still provide a benefit? Or maybe we've solved domain adaptation or domain generalization with these larger and more modern pre-training methods. Maybe we don't need that anymore. And the answer here is, can adaptation still help? The answer is yes, it still helps. But the caveat is that we saw bigger gains from older methods. Right, so here I'm highlighting the 2 rows which are using this method called CDAN, which is now, you know, I think it's like 5 years old, so not very recent, not the state of the art in as far as papers go, and as far as the standard evaluation using ResNet and ImageNet 1K pre-training go, it's not the best. But when we test it with this more modern backbone like SWIN large or Connex X large, it actually is the one that on average provides the best performance compared to all these others. So source only is no adaptation. So we go from about 45% to about 50, 51%. So there's a sizable gain from doing adaptation. But not, it's doing better. So that's not always the case, right? So if you look at this kind of MCC method, it's not improving by as much or not even much at all, depending on the backbone. So the takeaway for me is that, you know, these more recent adaptation methods, they underperform the older method CDAN, I think because they've been tuned a little too much to the older pre-training with ResNet and ImageNet 1K. And I think we need to be very careful of that. So we should, I mean, it's good to compare to the same baselines in the paper, but we also should compare to more modern pre-training to see if our method will still provide an improvement. And I'm not going to talk about the details of any of these methods, but you're welcome to check the paper, and you know, it cites all of these methods if you're curious. Okay, that's it for this paper. I'm going to move on to the next one, but I want to pause and see if there are any questions.
I guess nobody else is asking. Maybe I can see.
Hi, can you hear me? I have a question regarding this interesting result of the domain adaptation techniques plus the pre-training. So
Yep.
do you have some results on, say, given the, like, compare with naive, say, ERM training or the source only in this column, and also say CDAN, when scaling up the pre-training like model size or scaling up the pre-training data set? say how, as the scaling goes on, like how does it like change?
Yeah, that's a great question. So we didn't run that specific experiment, but we did run generalization. So generalization means we just train on the source data and test on the target, and we don't apply CDAN. And in that setting, that's what I was showing earlier. It does help to have a larger model, so more parameters, and to have more data with some caveats that I mentioned. But we didn't run, just because there's only so much we can do on the cluster in a
Yes.
limited amount of time. But I think it would be a good experiment to try. And I predict that it would still help to have the larger pre-training. But it could be that the improvement is less, right? So if you basically, my prediction is that you can improve O.O.D performance in two ways, either by increasing the size of your pre-trained backbone, or by improving your adaptation model. Well, I shouldn't say or, both, right? You can do it in both ways, right? But if
Yes.
your pre-trained model is weaker, your adaptation model potentially can give you more improvement. And as you supersize and strengthen your pre-trained model, your adaptation model might start giving you less improvement. And this is something that I think, people who work on domain adaptation methods don't always want you to know, right? Like we like to show off our method in the best possible way. So this could be also one of the reasons that people are slow to adopt the stronger backbones. But I think it's important that we adopt them.
Yeah, I think the point is, I think the scaling, I think there's two results here. This one is a very large network on probably a larger data set. And on the other hand, probably is ResNet 50 with pre-trained on ImageNet 1K. And there probably CDAN is less performed than other methods. But as the model size scaling up, probably there's a different trend of different methods. I will say, like, if there's one approach, say the CDAN or some other approach, can scale with the scaling up, that aligns pretty well with the pre-training size or pre-training model size or data sets. If these two align well with each other, that would be a good thing to have. Say just
Yes, I agree.
Yeah,
Yeah.
thanks.
Yeah, that's a great point. Okay, I think there's another question. Feel free to unmute and ask, or put it in the chat. Oh, maybe not. Okay. Okay. Is it possible to use neural architecture search for designing a better backbone? Yes, that's certainly possible, and people are working on that. But I guess maybe to me the more interesting question is it possible to design a better backbone in the sense of better generalization to out of domain data? And I think most work, again, as I was mentioning, 99% of all machine learning papers test IID. And I think that that's also the case for neural architecture search. And I think it'd be interesting to look more at the O.O.D performance and looking for architectures that are better for O.O.D performance. I'm not going to say that work doesn't exist, because I'm sure I'm wrong and it does. Someone will point it out. But I think that is, to me, the more interesting application of neural architecture search. All right, so great. Great questions. So let's move on to the next part of my talk, which is now we're going to talk about a different type of data set bias, which is it's still a domain shift, but one that introduces spurious correlations into your model. So here's an example of this kind of data bias, right? So the bias here comes from the fact that we have males and females, and we're trying to predict, is the person wearing heavy makeup or not? right? So the two categories that it's a binary classification problem, right? So the top male and female wearing heavy makeup examples, and the bottom are male and female not wearing heavy makeup. And so, okay, fine, so we have data like this, we can train a model. But if we collect a data set like this in the wild, right, without taking too much care to balance everything, we'll probably end up with a big imbalance towards females wearing heavy makeup, right? So most of the heavy makeup examples will be female as opposed to male, right? Maybe that's changing these days, or maybe if we, go only to heavy metal concerts and take all of our pictures there, but then we'll have a different kind of bias, right? And so this is kind of, again, this happens naturally. There's nothing adversarial here. This is just the distribution of data, and like there's some correlations, but it doesn't mean that our models should learn this correlation, right? So, and specifically, the model shouldn't predict heavy makeup based on the gender, right? But that is exactly what happens. If you train it, and lots of papers shown this, if you train the model with ERM on this kind of correlated data, it will cheat, right? Because it's easier for the model to lower its training error this way. So it will cheat by learning that, especially if it's an easy attribute to predict, like female versus male, it will use that attribute, like or long hair or whatever, to cheat and predict the heavy makeup attribute based on that, rather than the actual, makeup features. All right. So that's the problem. And so what we're looking at with my colleague Brian Plummer at BU and our PhD student Mon, we've been looking at this issue of, okay, how do we mitigate this bias? And the solution that we came up with is actually quite simple. It's just based on resampling the data, right? So again, we have bias data for training. So here, actually, the attribute we're predicting is hair color, so black or not black. And the groups that the data set is biased on are male and female, so again, on gender. Right, so if we train a deep learning model directly on this data set, it will learn a spurious correlation between hair color and gender, right? So it will just predict black hair if it sees female, if it recognizes that it's female, and it will predict blonde hair otherwise, or non-black hair otherwise. And so there are actually some simple ways that we can deal with this just by resampling the data set, right? So in this case, we take the original data set and undersample it. By undersampling, I mean we remove examples until the groups are balanced, right? So we have the same amount of female and male examples for both black and non-black hair. Right, so prior work has looked at this, and it can be effective. However, it has this downside that we're throwing away data now, and potentially a lot of data, right? If there's an extreme, like 95 to 5% imbalance in the distribution, then we could be throwing away 90% of our data. That's not good. So instead, what we proposed is a slightly different way of resampling the data set that we call bias mimicking. So the idea here is to resample the data set twice. Both times we are going to mimic the bias. So the first on the left, we're mimicking the bias of the non-black hair category, which has more male than female, but for both black and non-black hair. Right, so you can see the bias is mimicked across both categories of predicting. Okay, but this would still throw away data. So in order to not do that, we create another data set where we now mimic the bias going in the opposite direction. So the original black hair bias, where we have more female than male. And then we train the model on both data sets, right? So we have, we alternate, or we use batches from both data sets. And what that does is it removes the incentive for the model to learn the spurious correlation because it no longer helps the model reliably to lower training error. Okay, so that's kind of a simple idea, but it turns out it works surprisingly well. In fact, it works as well or even a little better sometimes than much more involved, like kind of more complicated model-based approaches where you're changing the training loss or you introducing more hyperparameters or you're actually training the model in a different way than just the standard training. So here all we did is just we changed the data set itself and the model doesn't change. Okay, so just to summarize, we saw that this kind of simple resampling method, in fact, even undersampling and oversampling, other methods that we tested are actually pretty competitive on these bias mitigation benchmarks. And then we introduced this new method called bias mimicking that has consistent competitive performance. So vanilla resampling that we tried sometimes don't work that well, but bias mimicking consistently does as well as the state-of-the-art model-based methods. Okay, so I'm not going to go into too much detail, but we have essentially these standard benchmarks that we look at. So the first one is UTK face. The second one is Celeb A. So this is where we have faces and we're trying to predict things like age, race, and hair color, as I mentioned, blonde or non-blonde hair color. And vanilla here just means we don't do anything. We just train the model on the bias data set and we see there are two metrics here, UA and BC. So these are metrics. UA is unbiased accuracy and BC is bias conflict. So with these metrics, the goal is to improve them. And you see that, with vanilla, we still have a ways to go. And then there are these existing methods that we're comparing to. In the middle group, these are model-based methods. And then the last group is resampling methods. So nothing to do with the model, just resample the data set. And here we have oversampling, underweighting, and undersampling. Underweighting is where we assign different weights to the training data. And if we look on average performance, right? So the last two columns are average performance. So here, this bias mimicking approach that we introduced actually does quite well and is comparable in the UA metric to the best model-based methods, right? So, and it's even better on this BC metric, the bias conflict metric. So the point here is, again, this is kind of simple pre-processing method and yet is competitive. And so we think that it should become kind of a new standard baseline in this line of work. Right, we also compared to another set of methods. So somehow these approaches are a little bit fractured against across different papers use different data sets to compare with each other. So this group of method, they use a data set called color bias CFAR or CFAR-S. So the bias here is, so some of the categories are grayscale, artificially introduced bias. Some of them are grayscale and others are color. And so if you train, again, vanilla, an N-wave softmax vanilla model, it will learn to correlate some categories with color and it will, again, cheat. And the metrics are also unfortunately different with this group of methods. It's just how things have evolved in the literature. But again, so here bias amplification lower is better, and we get a pretty low number with undersampling on this data set. compared to a bunch of these model-based techniques. And then color, so color and gray are the two groups. And we want high accuracy on both, right? And we want high average accuracy across both groups. And again, our method does, and competitively, compared to this DI. So this is a method called domain independent classification, which is a state-of-the-art method. So great. Okay. So I'm going to move on from this. I'm going to see if there are any questions. I didn't see any. Okay. Oops, having trouble here. So the last thing I want to talk about is, well, what happens when our downstream task that we care about, downstream meaning not the task we pre-train the model on, but the one we actually care about. What happens if it's a kind of rare in the sense that it's rare to find data like that on the web, which is where most of our pre-training data comes from, right? So ImageNet comes from the web, Lion and all of these Flickr, large or JFT, all these data sets come from the web. But what if our downstream task is chest X-ray classification or fine-grained flower classification? There are not so many fine-grained categories that you can find online, or something like satellites. Right? So lots of examples of tasks, visual tasks that don't quite match the online data distribution that you find in ImageNet and other online data sets that we use for pre-training. So I wanted to mention this paper where we looked at what happens if you what if we can use synthetic pre-training for such tasks, and maybe we can even tailor the pre-training data to improve performance. So this doesn't really address domain generalization or adaptation directly, except that we're going to be pre-training on synthetic data and transferring to real data. So that is a type of domain shift. And we're going to show that actually we can do pretty well with just pre-training on synthetic data. And this, I should say that first author is Samarth, a PhD student in my lab, and this is joint work with all these folks. And so what we want to do is, can we customize the pre-training data, right? So instead of using the same pre-training data for all these downstream tasks, can we customize? We're going to customize it by generating custom pre-training data using simulation, using synthetic, Unity or some CG engine to generate synthetic data. Right, so if we just take a bunch of models, 3D models of objects, we can generate the synthetic ImageNet is what I call it, right? So it kind of looks like ImageNet, but it's completely rendered in simulation. So we have different backgrounds, we have different poses, different objects. But what about the way we do this? What about kind of the size of the object, how blurry the image is, what the lighting is, what the background is? These are all now controllable parameters in our generation. And so we wanted to see if these parameters affect accuracy on downstream tasks. So we're going to generate data using different settings, pre-train the model on that data, and then tune it on the downstream tasks. Okay, so we have these 4 downstream tasks: Eurosat, SVHN, Sketch, and DTD. And so we're here reporting downstream accuracy when pre-training on all these variations of synthetic data, right? So the first one just varies pose, the second one adds lighting variation, then blur materials in the background. And the interesting thing is you see that the best performance varies quite a bit, right? So for Sketch, adding background actually lowers performance. Adding background variation lowers performance. So this led us to think that maybe we need different pre-training data parameters to favor different tasks. Because clearly choosing the parameters in a different way can improve performance on downstream tasks. So we propose this method that we call task to sim, where just very briefly, because I'm almost out of time, we embed the task into vector space using an existing method called task to vec. And then this embedding is fed into our task to sim model, which predicts which simulation parameters to use. And then we use those generated simulation parameters predicted by the model. We use them to generate the pre-training data. And you see some examples here. So varying like the size of the object, varying the texture of the object, varying the background, varying the lighting. Okay, and then this data is generated, and then we pre-train the classifier. And there's a loop here where we then construct the downstream model and evaluate, and that gives us a reward, which is used to update the parameters of the task to sim model. So this reward comes from evaluating accuracy on downstream tasks. Okay, so I think this is basically my last slide. This is just one summary of some results that we got, and I encourage you to look at the paper if you're interested in more detail. But here we're comparing pre-training data sets. So the first row is pre-training from scratch. The second row is just randomizing the pre-training. So pre-training from scratch means we don't use any pre-training, we're just there's no pre-training essentially, right? So train everything on the downstream data set. Random means we randomly initialize. Domain randomization means we are using parameters to generate our synthetic. So this is synthetic data, but the parameters are chosen at random. And ImageNet is just ImageNet pre-training, and task to sim is our method. So task to sim compared to domain randomization actually chooses the best simulation parameters. Okay. And here we are looking at tasks that were not seen in training task to sim. So it's generalizing to new tasks that it wasn't trained on. And you can see that there's some improvement compared to ImageNet in many cases, like in fine-tuning the models, for example. So we think that's promising, and we're still working on this. We have some follow-up directions that we're investigating. All right, I'm going to pause here. This is the end of my talk. I want to see if there are any other questions that I can answer.
Do you like in the like when optimizing the parameters, the simulation parameters, is like this feels like a meta learning kind of objective, like since we are training a downstream model and gradients are back propagating from there. Like is there a task level overfitting? Like even if at a training time the embeddings actually, like the sort of like the optimization process actually end up maximizing the reward or improving the performance, like is it like, did you see a big gap, like very high level of overfitting? Like your next slide does show that there are benefits, but were the benefits for the training task much higher, or is it like there's no overfitting, it just generalized very well?
It's a good question. Yes, so you're right that it's a kind of meta learning setup, because we're learning to predict simulation parameters on a bunch of downstream tasks, and then at test time we might be given new tasks, right? We don't have to use the same tasks at test time. And here a task is a data set with some labels. And at least from our initial results in the paper, we see that when we test the task to sim model on unseen tasks, it's still generalizes well, right? So it's outperforming randomization. It's even outperforming ImageNet pre-training. This is controlling for amount of data. So ImageNet pre-training has a star because we're limiting it to the same number of classes and the same size of data. So it's 100 classes, 40K, or 237 classes, 100K. So yeah, I think this is at least some indication that the parameter selection generalizes. But that said, it's a limited benchmark. I think it's like 11 different tasks. So, with that caveat, I think at least initially it seems like it does generalize.
Yeah, I guess that's what matters at the end, like it should generalize.
Right.
But yeah, I guess likely there isn't much of it in there. Since the generalization in many cases, like it's going from 72 to 87. So there is.
Yeah, so one thing we noticed, for example, it might learn to either blur the pre-training data or not blur it, right? And that's the kind of thing that it's predicting based on the new task. But again, like this, we may not have a big enough coverage of tasks in the current training data set. And I think we need to test with more tasks, essentially, to confirm this.
Mm-hmm. Yeah, that sounds good.
Great, thanks for the question.